This is 9.5b notes, alternating series remainder. For a convergent alternating series, the partial sum, the nth term partial sum, S sub n, can be a useful approximation for the sum S of the series. The error involved in using the nth term partial sum is the remainder R sub n, which is the total sum minus the nth term sum. So basically we can find, after we find a particular specific partial sum, we can use that to determine the error bound for the actual sum. Let's look at the definition here. Suppose an alternating series satisfies the condition of the alternating series test. So we know that this is going to be a convergent series, convergent alternating series. Namely that the limit of a sub n as n approaches infinity is equal to 0. So we know that each term is going to continue to get smaller until it reaches 0. And also that the rule of sequence is not increasing. So if the series has a sum S, then the remainder is going to be the sum minus the nth term sum. We know that the difference between the sum and the nth term sum will be less than or equal to the n plus first term, where S sub n is the nth term partial sum of the series. So in other words, if an alternating series satisfies the condition of the alternating series test, we can approximate the sum of the series by using the nth term, nth partial sum S sub n. And your error will always have an absolute value that is not greater than the first term that is left off. So if we find the sum of the sixth partial sum, then the seventh term will be the maximum error for the actual sum. So the a sub n plus 1 is going to be the first unused or the neglected term. So to kind of give you a visual, we know that if we have an alternating series that is going to be convergent, then we know that what's basically happening is that we are adding and subtracting values, but each value is going to get us closer and closer to the sum. So that will have to be a given fact. And because of that, we know that with each term, each value that we get, each partial sum that we get, the next term will tell us how far away, or the maximum error that the sum can be. And the reason that we know that is because we know that each term is going to get us closer and closer to the actual sum. Okay, so that's how we know that the nth term partial sum is always going to be within plus or minus the remainder value, and the remainder value will always be the first neglected or unused term. So if we look at example 2, approximate the sum we have the alternating series -1 to the n minus 1 over n factorial by using its first 6 terms, and find the error. Use your results to find an interval in which the sum must lie. Okay, so first off, we know that this sum is going to be a convergent series because 1 over n factorial, the limit of this rule of sequence will give us 0. So what we can do is, if we want to find the first 6 terms, we can just add up all the 6 terms. So, but we can use our calculator for that. So the calculator, we can plug in the rule of sequence from 1 to 6, and then we can find the sum. We can just plug all this into our 83 or 84 Ti, and the sum, the sixth partial sum, gives us 0.6319. And if we find the first 6 terms, then we know that the maximum error will have to be the 7th term, because we know that each term is getting closer and closer to the actual sum, and the seventh term will overshoot the actual sum, but but we know that the error cannot be any greater than the first unused or neglected term. So that means the first left off term will have to be negative or absolute value of 1 over 7 factorial. Okay, and 1 over 7 factorial is 1.98 times 10 to the negative 4. So we know that this will have to be the maximum error. So we know that the sum must be therefore within the range of this of that error. So we can say the sum is going to sit between 0.6319 plus 1 over 7 factorial and between and also minus 1 over 7 factorial. So this will be the smallest that the sum could be, and this will be the largest that the sum could be, is because this seventh term will produce the error bound for our infinite sum, our series. Let's do example 3. Approximate the sum of the following series by its first 6 terms. So if that's the case, then we know that the seventh term will have to be the first unused, neglected term. So therefore, the seventh term will produce the remainder or the error bound. Okay. So we know the sum of the series, therefore, must be s sub 6, and this is similar to what we saw before here. The remainder, therefore, is going to be less than or equal to the first neglected term, which is 1 over 7 factorial, which is 0.002. And the sum of the series is therefore between 0.63194 minus 1/7 factorial and between 0.63194 plus 7 factorial, 1 over 7 factorial. Okay, so basically example 2, which is having to, now we can just combining these values together to show numerically that the sum is going to be sitting between these two values, okay, based off of the fact that we're using the first 6 terms. Okay, of course, we can get a better and better approximation if we found more, if we increase the number of terms, or if we found a higher nth partial sum. Okay, example 4, approximate the sum of our infinite alternating series with an error that is less than 0.001. Okay, so if we write out the first few terms, if I plug in 1, I'm going to get 1 over 1 to the 4th. If I plug in 2, I'll get negative 1 over 2 to the 4th, and then plus 1 over 3 to the 4th, minus 1 over 4 to the 4th, plus 1 over 5 to the 4th. And if we plug these values in our calculator, we see that these values are going to be larger than 0.001. Okay. So basically, if we're able to arrive at a value, a term, that is less than 0.001, then we know that that term can act as the error, the appropriate error bound for the partial sum. So if we plug 1 over 4 to the 4th, that's greater than 0.001, so we keep going. 1 over 5 to the 4th, that is still greater than 0.001. Now, when we plug in 1 over 6 to the 4th, that's when we get 7.716 times 10 to the negative 4. And if we move that decimal 4 places to the left, we get 0.000716. So this is going to be the first term that is going to be less than 0.001. So we basically want this to be the first unused term for the sum. Okay, so if this is the first unused term, then that means we can find the sum of the first 5 terms and still get a value that has an error that sits less than 0.001. So if we add up these 5 terms, the fifth partial sum, we're going to get 0.947, which is going to be, we know, within the error bound of 1 over 6 to the 4th, because we see the error here is less than, where that value is less than 0.001. All right, example 5, determine the number of terms required to have an error that is less than 0.001. So we basically want to find out when is this, for what value of n will this rule of sequence produce a value that is less than 0.001. So we want a value that, we want a rule of sequence where the n value will produce a fraction that is less than 0.001. So we can just solve for n by setting these two values equal to each other. And if we do cross product, we get 1 is equal to 0.001 times 2n minus 1. We distribute to the 0.001 through, add like terms, and we see that n is going to be equal to 500.5. So that means n has to be at least 501 terms in before this error or this term, this value will be produced. Okay, so that means we have 501 terms required in order for this sum to have an error that is less than 0.001. All right, next thing, we do the same thing. 1 over, we want to find out when is this rule of sequence going to produce a value that is less than 0.001. So here, I would just do guess and check. If we do n equals 5, or n equals 4, or n equals 5, we see that will produce a rule of sequence that is greater than 0.001. It is only when we hit n equals 6, that's when we have 1 over 7 factorial, which is 0.000198. So this is going to be the first term that will produce a value that is less than 0.001. So that means we know the number of terms required in order for this condition to be met is where n is going to be greater than or equal to 6, or you can say n is greater than 5.